let's have a chat about APs. Okay, so APs are the first type of sequence that you cover in AS Maths. You're going to cover APs, GPs, and binomials, but this lesson is going to focus just on having a look at those APs and getting to know them properly. So a little bit of a background, we're dealing now with sequences. Okay, so what is a sequence? Okay, it is a collection of numbers, it's a set of numbers, but what's important is that a sequence is a set of numbers in a given order. It's not just a random collection of numbers. So we're talking things like 2, 4, 6, 8, hopefully familiar. -3, -4, -5, -6, even something like 10, 15, 20, 25. Each of these represents a sequence. Okay, so we have sequence A, sequence B, and sequence C. 3 different sequences. They are very short little sequences that we've got here, but they're enough to work with for now. The other term that you need to be very familiar with when it comes to sequences, series, progressions is term. What is a term? And a term is very simply one of those numbers in that sequence. So a number, a particular number in a sequence. So 4 is a term, 6 is a term, -5 is a term, 10 is a term. Okay, so the number that is in the sequence is called a term. Now we're going to be working a lot with terms, so we have a special set of notation associated with them, and we call them U. Okay, so a lowercase u, that is our representation for a term. And what's really cool is we can actually refer to a specific term. So for example, 4 here is the second term in this sequence. So we would call it U2. This is the second term. So we know we're talking about a term because we have a little u here. And then the subscript number, so it must be below your line, that tells us which specific term that we're looking at. So we could have the -5, okay? That is a 1, 2, third position. So it's the third term. It is U3 equals the third term. And then, of course, we have that term where we don't know what it is. So if we think about sequence C, we know that 45 is going to fit in that sequence if we keep going, because we're counting in 5s, and 45 comes in. So, but we don't know where it sits. Okay, so we could figure it out, but we can also say we don't know what it is, and that would be UN. So UN is the nth term. The term with a position that we don't know. We know that 45 is part of sequence C, but we don't know which term it is. Therefore, it is a UN. It would be an nth term. So our nth term can be an expression or a term we don't know. We're going to get more into how we actually play with that a little bit more in a moment. So we've got the sequences, we've got terms, okay? And we can identify the terms using our subscripts. So let's have a little bit more now, a focused look on APs themselves. So APs. The world revolves around addition for an arithmetic progression. Okay, so we are adding the same number over and over and over again. And remember that in this world, there's no such thing as subtraction, okay? Because subtraction is simply the addition of a negative number. So we can have positive or negative values. So if we think about our sequences A, B, and C, okay? So A was 2, 4, 6, 8. So here it's all about adding 2 every single time. -3, -4, -5, -6. Our sequence B, that one was all about adding -1. Okay, because we are subtracting 1 each time, but that is always thought of as an addition for this sort of thing. So C was 10, 15, 20, 25. So this one is all about adding 5. So it is the same sort of thing. We would take this one to -1, but it's that concept of this repeated use of the value of -1. And what is really important is that we're actually going to build this into a standardized set of features of a sequence we can then use for calculations. So what are those features? Every AP we work with is going to have an A, which is the, let's make a bit more space, we'll put them over here. So A equals our first term. So for sequence A, it's a 2. For sequence B, it's a -3. For sequence C, it's a 10. Okay, there is always a first term, and we always call it A, not U1. Okay, A is our first term. There is always an N, which is our number of terms. Sometimes we don't know it, but there is always a certain number of terms. In each case here, we have 4 terms. So N equals 4 for sequence A, B, and C. And then our special one is our common difference, which we call D. So D is what we call the common difference. And that is the number that we're going to add every single time. So our +2, our -1, our +5. Those are the common differences for our sequences A, B, and C. These are the 3 letters that your life is going to revolve around when it comes to APs. A, your first term, N, your number of terms, and D, your common difference. Now, you're going to see it in your textbook, so I'm not going to pretend it doesn't exist. You also have something called L, lowercase l, which is the same as UN, which is the same as the last term. Every now and again, this pops up. Every now and again, once in a blue moon, you get a question that tells you the last term. And yes, you could use L, but you could also use UN, okay? And the whole sort of everything that we're going to focus on just now is all about UN. So it makes a whole lot more sense to think of things in terms of A, N, and D, and actually not use L so much. The formulas related to L are in your formula sheet. There's absolutely nothing stopping you working with them and using them if you understand them and you can see how they all fit in. But if you've got the slightest bit wobbly, then please just focus on A, N, and D for your APs. So what do we do with A, N, and D? APs, GPs, binomials, we have the same theme running through everything that we do with sequences at AS. It's all about working with particular terms or particular sums of terms. So we might be working with the 3rd term of this sequence. We might be working with the 25th term of that sequence. We might be working with the sum of the first 10 terms, or the sum of the first 3 terms, or the sum of the first n terms. Okay, but it's always about pulling out of that sequence and only working with some of it. So if we have a look at our starting sequence A, 2, 4, 6, 8. We know our first term, A equals 2. We know that in this case, N equals 4, and we know that D equals 2. Each time we add 2. Now we can say, okay, well, that's cool. If we wanted to do something with the third term, we can look at it and we can say U3 equals 6. We could look at this and we can even get the sum of terms. We can take our 4 terms, we can go 2 plus 4 plus 6 plus 8, and that's going to give us 6 and 6 and 20 is our sum of terms. We could say, even in a more experimental world, let's say we said if we increase this to 5 terms. We could then say U5, what would it be? Well, we just add 2 again. 8 plus 2 is 10. And we're quite happily going along with this, but there's a catch, right? There's always a catch when things are simple. This is all very well and good when we have 4 terms. Life is nice and small and simple. But what if we have 100 terms? What if we want the sum of 50 terms? Are we really going to sit and write out all 50 terms and then add them all up? That seems very inefficient. And maths doesn't tend to be inefficient. We're working on that, you know, let's make the most efficient, the best way to get to an answer. Now we want to add in all this inefficiency. So we're going to make life a little bit more fun. So this we can brand as inefficient. If you can spell inefficient, it does help. Okay, particularly because lots of terms, this approach doesn't give us any way of dealing with it. And it's something that you bumped into when you did IG. You always worked with sequences with very small numbers of terms. So now we're going to simplify our world. Wonderful. Our AP, right? It's very reliable. It's very predictable. It's adding 2 every time. When something is reliable and predictable, you can summarize it. You can condense it. You can create a formula. So, we have said that this is all about working with specific terms, working with specific sums. So, to work with a specific term for an AP, obviously we're going to have different formulas for GPs and different formulas for binomials. For an AP, UN equals A plus N minus 1 times D. And SN, that's a capital S, equals 1/2 N 2A plus N minus 1. Ooh, times D, not times bracket. So again, this is where that other formula of using L comes in. We've got an SN formula using L, but we tend to avoid it because this one is a more powerful one. This works whatever the sequence. Whereas your one using L only works if you know that last term specifically. So what is UN? UN is our nth term. But if you change that to a 5, you change that to a 5, now you can calculate the 5th term. If you change this to an 8, change that to an 8, now you can calculate the 8th term. Change this to 100, change that to 100, you can calculate the 100th term. So it's all about now being able to go in and target that specific term in our sequence. Okay, and what is Sn? Sn is the sum of a particular number of terms. So the sum of n terms. So if you want the sum of 10 terms, that becomes a 10, that becomes a 10, that becomes a 10. Okay, so we use our identifier to figure out what to put in our formula, and we can get the sum of n terms. So our identifier here tells us which term we want or how many terms it is that we're summing. And then we can use our values for A, for N, for D, for N, for A, for N, for D, and you see the repetition. You see why I say life for an AP is all about terms, sums, A, N, and D, because everything in the world can be reduced to A, N, and D. It's really important that you are very comfortable with these formulas, because we're going to use them in every direction. We could be given A, N, and D and we're calculating a term, or we could be given the term A and D and we have to calculate N. Okay, so whenever you get a formula, as you've already discovered most likely in AS Maths, whenever you get a formula, you can use it in any direction. You are not restricted to just calculating one thing. So yes, these formulas are in your formula sheet. They are available to you in exam. So, but all that means is that there is no excuse for getting them wrong. In terms of being comfortable with them, you still need to be fully familiar with them. When you're reading a question, formula needs to pop into your head so that you know exactly how all the information that you've got works out. So it's really important that you don't just say, oh, it's in my formula sheet, I don't have to memorize it. You do need to memorize it, because that's the level of comfort that you need to have with formula. And then when you see it in questions, when you see these pieces of information coming out in a question, you know, this is where I'm heading. This is what I'm going to use. Okay, so let's do a few examples. We've got a bit of time to play with, so we can see how these sorts of things work. So we'll start out with our series A that we had going earlier on. Let's say we have 2, 4, or that is a 4, promise, 6 and 8. But now let's make it longer. 10, 12, 14, 16, lots and lots and lots. We're going on and on and on with the sequence. Okay, and we say, what is the 12th term? So we've got to first stop and we've got to say, okay, what information do we have? Okay, we have A equals 2, the first term. D equals, well, the difference. 4 minus 2 equals 2. And N in this case is 12, because we've been asked for the 12th term. So it would be U12. So U12, our 12th term, equals A plus N minus 1. So 12 minus 1 is 11 times D, which is also 2. And that is why it's also so important. Always, always, always substitute that value of D in brackets, because if it's negative and you don't put the brackets, there is no multiplication. So play safe, always substitute that in brackets. So 2 plus 22 is 24. So the 12th term of our 2, 4, 6, 8 sequence would be 24. But we don't have to sit and list them all out. We can just calculate. So another example, let's use the same one, 2, 4, 6, 8. Okay, so we did the sum of the first 4 and we got 20. Let's see what happens if we do the sum of the first 10. So we've still got our little summary of A and D. They haven't changed, but N has changed, because sum of first 10 would be S10. So N is now 10. So S10 equals 1/2 times 10, 1/2 times n. 2a is 2, plus n minus 1. 10 minus 1 is 9, times d is 2. So you can see we've got a whole lot of numbers. We can just evaluate. So we have 5 times 2 times 2 is 4, plus 9 times 2 is 18. So 5 times 4 plus 18, so 5 times 22 is 110. But we didn't have to sit here and go 2 plus 4 plus 6 plus 8 plus 10 and on and so until we had those first 10 terms and we're not losing track. We just like it into formula and it's so much better. And that is why I believe AS sequences are so much better than IG sequences, because the world is a whole lot simpler. Even when it gets fun and games, even when things get a little bit more complicated, it still is straightforward use of these formulas. So let's do an example of that more fun and games and a little less straightforward. Let's take a sequence. Our sequence can be 5, 10, 15, and so on. Okay? And let's say, in this case, we are told that Sn equals 275. And they want to know, what is n? What's the number of terms in this sequence that would give us the sum of 275? We work through the same thing. We've got A equals 5. We've got D equals 10 minus 5 equals 5. And we've got Sn equals 275. But that doesn't help us. It is just format like that. We need to break that down because life is all about A, D, and N. So 275 equals 1/2, N we don't know. 2A would be 2 times 5, plus N minus 1 we don't know, times D would be 5. And now when you look again, you can see the magic starting to happen. We have an equation with one unknown. So we can do a similar thing if we're given a term value. Okay, we can say, okay, the 20th term is 257, and then we can work backwards and find A or D or N. Okay, so in this case, 275 equals 1/2 N, 2 times 5 is 10, plus 5N minus 5. Beautiful multiplication. So it opens the bracket nicely. And then we can go ahead and we can solve and we can simplify. So clearing our fraction, 275 times 2 is 550 equals n, and then 10 minus 5 is 5 plus 5n. So 550 would equal 5n plus 5n squared. We have a quadratic. Everything is a multiple of 5, so we'd rather make our life a little bit easier. N squared plus n minus 110. And you will very quickly learn that their aim when you're working with APs, GPs, and binomials is not testing so much your quadratics. So generally they are straightforward to factorize. Factors of 110 that subtract to give 1, 10, and 11. Okay, we want a plus n, so we want plus 11 minus 10. So we have n equals minus 11 or n equals 10. And then you must turn your brains on. Because your brain must realize that in this case, n cannot be a negative number. Yes, it's a valid answer to our quadratic, but it is not applicable. We cannot have minus 11 terms in our sequence. So therefore, n equals 10 only. That's the only answer that is valid. If we go for 10 values, 5, 10, 15, 20, so 10 terms, and we added them all together, we would get 275. So it doesn't matter if we are dealing with terms, it doesn't matter if we are dealing with sums, it doesn't matter what it is that's unknown in this whole mix. We're using those two formulas, term formula and sum formula, and then we are pulling everything together in order to pick out what we have and then calculate what we need. So arithmetic progressions, all about addition, all about A, D, and